So let's take our fully charged capacitor, and now we want to use it. So we want to take advantage of the fact that it has charge on those plates. We want to let that charge generate an EMF that drives a current. And so what we'll do is we'll remove the battery, and then we'll connect a capacitor and a resistor in series. And then when we close our switch at t equals 0, the capacitor is going to act like a battery, right? It's going to generate an EMF that drives a current because there's a potential difference between these plates that will serve to discharge the capacitor. In our previous video, we had the battery over here, and the way we'd drawn in the battery would have charged this as the positive plate and the negative plate. Well, that means that once we go to discharge this series RC circuit after we've removed the battery, it's going to drive current back in the other direction. So from our positive plate, it's going to drive around towards our negative plate. Because there's a finite amount of charge on the capacitor, it can't drive that current forever. And in fact, the current in our circuit, as the capacitor is discharging, decays exponentially just like it did when we were charging the capacitor. The reason is very different. When we were charging the capacitor, the current decayed exponentially because the capacitor was increasingly acting like a battery that generated a back EMF that was canceling out the current being driven by the battery. Here, we simply have a finite amount of charge on the capacitor. And so once that charge is gone, the capacitor doesn't have an ability to drive current anymore. The current decays in a similar way when we're discharging the capacitor as it did when we were charging the capacitor. Again, if we want to think about that initial value of the current, we're going to play the same game, which is basically we want to think about what's going on at t equals 0. At t equals 0, we're going to let capital V be the potential difference between the capacitor plates. So notice we don't have a battery in our circuit anymore. The capacitor is what's acting like a battery, and so the V here is whatever the initial potential difference was between the plates when they were fully charged. Again, using our loop rule, well, we can see there's only two elements at the instant we close this circuit. So whatever the potential difference is between the plates, you've got to drop that same voltage as the current runs across the resistor. And again, we know how to calculate that out. That's going to be whatever that initial current value is times the resistance of the resistor at t equals 0. And so we solve for exactly the same expression with the big difference that, of course, this isn't the V of the battery anymore. This is the V of the initial potential difference between the plates and the capacitor. But we can plug that into our equation, and so we get that same solution for the current as a function of time. It's going to be equal to the initial difference between the plates of the capacitor over R times our exponential decaying term e to the minus t over RC. So just like we did before, we can define the time constant to be tau equals R times C. So again, the resistance of the resistor times the capacitance of the capacitor. And so I can rewrite this current as a function of time as V over R times e to the minus t over tau. And so this gives me sort of the same 3 points in time that we were interested in looking at before. And so what you'll notice is, again, at t equals 0, current through the resistor is equal to V over R. It will have dropped to 36.8% of that initial value after one time constant. And basically, if you wait long enough now, so as t approaches infinity, no current continues to flow through the circuit because all the charge has run off the plates. Once we know the current, we can calculate the voltage across the resistor as our capacitor is discharging. Again, that's just going to be given by the voltage of the resistor is equal to current flowing through the resistor times the resistance of the resistor. And so when we plug that in, again, we get the same solution we did before. It's just that, again, V here is the initial potential difference between the plates of the capacitor. So initially, we see the maximum voltage drop across the resistor. As the charges run off the plates of the capacitor, the current decays which means that the voltage across the resistor decays. And after one time constant, it has already decayed to 36.8% of its initial value. Again, if you wait long enough, because there's no longer any current flowing through the circuit, there's no voltage drop across the resistor. So the voltage drop across the resistor decays away to zero as all the charge runs off the plates. If we want to think about the voltage across the capacitor while it's discharging, again, our loop rule in this case tells us that the voltage across the capacitor has got to be equal to the voltage across the resistor. So here's the first thing that does change. When we were charging our capacitor, the voltage across the capacitor increased. This equation right here from our loop rule tells us that if the voltage across the resistor is decreasing because the current is decreasing, then so is the voltage across the capacitor. And again, that makes sense because as charge runs off the capacitor, the fundamental equation for capacitors, Q equals CV, tells us that if you've got less charge, you're going to have less potential difference between your plates. And so what we see is that we have exactly the same expression here for the voltage across the resistor and the voltage across the capacitor. The capacitor acts exactly the same way as a function of time as the voltage across the resistor. It starts at its maximum value. After one time constant, it's dropped to 36.8% of that initial value. And as charge runs off the plates, eventually the voltage across the capacitor also drops to zero. All this is happening, of course, because charges are leaving the plates. And so what we see is for the charge, it also decays. And it decays in exactly the same way as all these other functions. So it starts with the maximum charge on the plate. So at t equals 0, the charge on the capacitor is at its maximum value of CV, but then that's going to decay exponentially. So it starts at its maximum value at t equals 0. It drops to 36.8% of its maximum value after one time constant. And again, wait long enough, the capacitor will have fully discharged, which means that there's no charge left on the plates. So summarizing the discharging series RC circuit, in some ways it's even easier, because basically what we have is our loop rule tells us that the voltage across our two elements, the capacitance and the resistor, have to be the same, and in this case they're both going to decrease. Charge will run off the plates, that will decay exponentially, so the current will decay exponentially, so these two voltages will decay exponentially. All of this will decrease as our capacitor discharges. The various expressions, again, they've all got the same e to the minus t over RC term, and the only thing that's really different is what's this initial constant sitting out front. For the current, it's V over R. For the two voltages, it's just the initial voltage of the capacitor. And for the charge, it's the voltage of the capacitor initially times the capacitance of the capacitor. In terms of the two special points in time that we tend to want to think about with these circuits that are changing, at t equals 0, everything is at its maximum. Maximum charge on the capacitor, maximum voltage drop across my two elements, maximum current in the circuit. Wait long enough, as t approaches infinity, everything goes to 0. No charge left on the capacitor, no voltage drops across either elements, no current left in the circuit.